Welcome back to our explainer on atomic structure. I'm so glad you're here. In our first part, we learned the basics. We saw that atoms have a tiny, heavy nucleus in the center made of protons and neutrons, with tiny little electrons zooming around it in specific paths called shells. We also learned that each shell can only hold a certain maximum number of electrons. Today, we're going to learn something absolutely fascinating. We're going to discover how these tiny atoms actually make friends, join together, and build the world around us. Here is our chemistry treasure map for today. We'll explore the quest for 8, see what happens when sodium meets chlorine, uncover the magic of valency, learn to write chemical formula, and finally, check out the periodic table map. Let's jump right in.
Part 1. The quest for 8, where atoms seek their perfect match.
Have you ever wondered why elements don't just stay by themselves? Like, why do they bother reacting chemically to join together and form brand new things, like water, or sugar, or the salt on your food? What is the real driving force behind this microscopic matchmaking? Well, the answer lies in the magic 8. You see, atoms want to have exactly 8 electrons in their outermost shell to feel perfectly happy and stable. Think of the noble gases, like neon and argon. They already have full outer shells. They're like peaceful meditating masters. They just relax and don't really need to react with anyone else. Other atoms look at them and think, wow, I want to be that stable too. Now, helium is a tiny exception. It only has one shell and it's perfectly happy with just 2 electrons. But for almost everyone else, 8 is the magic number.
Section 2. Sodium meets chlorine, a truly magnetic friendship.
Let's look at the perfect microscopic match. On one side, we have sodium. Sodium has 1 extra electron weighing down its outermost shell. If it could just lose that 1 extra electron, the full shell hiding underneath would become its new outer shell, and it would be perfectly happy. On the other side, we have chlorine. Chlorine has exactly 7 electrons in its outer shell. It desperately needs just 1 more to reach that magic number 8. Do you see where this is going? When atoms give or take electrons to get their magic 8, something super special happens. They turn into an ion. An ion is simply an atom that now has a positive or negative charge, all because it donated or accepted electrons. Remember, electrons have a negative charge. So if an atom gives away a negative electron, it actually becomes positive. And if it accepts a negative electron, it becomes negative. It's kind of like earning a special chemistry badge. Watch how the magic happens. Sodium kindly donates its extra electron to chlorine. This earns it a positive badge, becoming a sodium ion, written as Na+. Chlorine joyfully accepts that electron, getting a negative badge, and becomes a chloride ion, written as Cl-. Now, because sodium is positive and chloride is negative, they stick together tightly, literally like magnets. Opposites attract, right? Together, they form sodium chloride, which is the exact same common salt you sprinkle on your food.
Section 3. The magic of valency, or counting hands for friendship.
Valency is a very important word in chemistry, but honestly, it's wonderfully simple. Think of it as the number of available hands an atom has to hold on to other atoms. Officially, valency is the number of electrons an atom donates or accepts to have 8 electrons in its outermost shell. If an atom needs to give away 1 electron, its valency is 1. If it needs to take 2 electrons, its valency is 2. It just tells us how many connections it can make. Metals are very generous. They love to donate their outer electrons. Because giving away negative electrons makes them positive, they form electropositive ions. If they give away 1 electron, they have a positive valency of 1, which we call monovalent. This includes friends like hydrogen, sodium, and potassium. If they give away 2, they're bivalent, meaning 2 hands. Examples are magnesium, calcium, and zinc. And if they donate 3, they're trivalent, like aluminum, which gets a lovely 3+ badge. Now, before we look at the negative valencies, we need to meet a very special group in chemistry. Sometimes, atoms group together in a tight, permanent hug to share a charge. We call this special polyatomic group a radical. They behave exactly like a single atom with a charge, but they are actually a tiny team of atoms holding hands tightly. Nonmetals, on the other hand, absolutely love to accept electrons. This gives them electronegative valency badges. Monovalent ones accept 1 electron, like chloride or the radical hydroxide. Bivalent ones need 2 electrons to be full, like the oxide ion or the sulfate and carbonate radicals. Trivalent ones, like phosphate and nitride, need 3 whole electrons to reach their magic 8. So, whenever you see those minus signs, you know exactly how many electrons they took in. Okay, let's dive into a tricky little secret.
Some metals are a bit moody and exhibit something called variable valency. This means they can actually change how many hands they use depending on the situation. For example, iron, whose Latin name is ferrum, can sometimes give away 2 electrons to become ferrous, Fe2+, but other times it gives away 3 to become ferric, Fe3+. Copper does this too. It can act as cuprous with a +1 charge or cupric with a +2 charge.
Section 4. Writing chemical formula. The crisscross puzzle.
To build a neutral compound where all the charges cancel out perfectly, we use a brilliant trick called the crisscross method. Step 1, we just write the symbol of the positive ion on the left and the negative one on the right. Step 2, put their valency numbers on the top right, and then completely ignore the plus and minus signs. Just pretend they aren't there. Step 3, simply crisscross the numbers diagonally down to the lower right side of the other symbol. It's literally just like a fun puzzle.
Let's see this in action. For magnesium chloride, magnesium is Mg2+, and chloride is Cl1-. The 2 from magnesium crosses down to chlorine, and the 1 from chlorine crosses to magnesium. We never write the number 1, so the final formula is just MgCl2. Now, what's really cool about calcium sulfate is that calcium is +2 and sulfate is -2. When the numbers are exactly the same, they cancel each other out. So we just write CaSO4.
So the absolutely crucial point to remember here is about our friends, the radicals. If a radical group gets a crisscross number that is greater than 1, we must put the entire group in a safe bracket hug before adding the number. For example, in aluminum sulfate, aluminum's valency of 3 crosses down to the sulfate radical. To show that we need 3 of the whole sulfate group, we put SO4 in brackets and put the little 3 outside. So it reads Al2 bracket SO4 bracket 3. Same rule applies for ammonium phosphate.
Section 5. The periodic table map, where everybody lives.
To find all these amazing atoms and figure out their valencies, we use the periodic table. It's a beautifully organized chart that puts all 118 known elements in systematic order. And how do they decide the order? By their atomic number. The atomic number is quite simply the number of positive protons hiding inside the nucleus of that atom. Element number 1 has 1 proton, element number 2 has 2 protons, and so on. It makes studying chemistry so much simpler.
Here's a sneak peek at some of the first 20 elements on this map, from hydrogen at number 1 all the way to calcium at number 20. Getting to know their names, their short 1- or 2-letter symbols, and their atomic numbers will make chemistry your easiest puzzle ever. You'll see familiar friends here for sure, like oxygen, carbon, sodium, and chlorine.
Let's uncover the hidden secrets of this map. The horizontal rows going right across are called periods, and there are 7 of them. The vertical columns going up and down are called groups, and there are 18 of those. Now here is a super secret trick. For metallic elements, their group number tells you their exact positive valency. And for non-metallic elements, you just take their group number and subtract 8 to find their negative valency. The map literally does all the hard work for you.
And before we finish our map tour, we definitely can't forget the special metalloids. Elements like boron, silicon, and arsenic sit right between the metals and the non-metals on the table. They are super unique because they have a mix of properties. They act a little bit like metals and a little bit like non-metals, depending on the situation. They really are the best of both worlds.
We have covered so much amazing ground today in this explainer, from atoms desperately seeking their magic 8, to ions trading electrons, understanding valency, and mastering the crisscross method to write real chemical formulas. With your brilliant new understanding of how the periodic table works, you are officially a chemistry matchmaker. So I leave you with this final thought. Now that you know the crisscross magic, which perfect atom match will you create on your own next? Keep exploring, keep questioning, and I'll catch you next time.